In this module, we will study about the quantum mechanical treatment of the linear harmonic oscillator. Now, the first question comes, why we are talking about a linear harmonic oscillator? Actually, linear harmonic oscillator is a basic model for a vibrating diatomic molecule. Why do we call it linear? It is linear because the vibrations are taking place in one dimension, and that way it will be a model for a diatomic molecule. This linear harmonic oscillator is also known as simple harmonic oscillator. This is so because the vibrations of the oscillator are taken as simple harmonic. That means they are to and fro motions about the mean position, and these vibrations follow Hooke's law. Hooke's law is basically that when a molecule or when an oscillator is stretched, then it follows and goes back to towards its mean position, and the restoring force with which it is restoring itself to its mean position, that is proportional to the displacement. And the Hooke's law is F restoring is equal to minus kfx, where kf is the force constant for the linear harmonic oscillator. For such a linear harmonic oscillator, the potential energy is given by the relation V is equal to half kfx square, where x is the displacement from the mean position. How does this expression come? That means how one knows that V is equal to half kfx square. There is a classical treatment which is already given, and you can see that. Here basically that if there is a particle of mass m which is undergoing simple harmonic motion, then it obeys Hooke's law. As you can see here, F restoring is equal to minus kfx, but then according to Newton's second law of motion, F is equal to ma. Now these two forces can be equated, and the force is mass into acceleration, and acceleration can be expressed as d2x by dt2, and therefore by equating these two equations we get a resulting equation which is d2x by dt2 plus kf upon mx is equal to 0. Now if one tries to solve this equation, the solution of this equation is x is equal to a sine 2 pi nu t, where nu is the frequency of the vibration, and if we take its first differential and then second differential, we find that d2x by dt2 is equal to minus 4 pi square nu square x, or in other words, we have now another equation which is d2x by dt2 plus 4 pi square nu square x is equal to 0. Now earlier we had the equation which was d2x by dt2 plus kf by mx. Now from these two equations, if we equate them, we get 4 pi square nu square x is equal to kfx upon m, or in other words, frequency of the vibration. That means in the case of a simple harmonic oscillator, the frequency nu is given by 1 upon 2 pi square root kf by m. So this is a very important expression which we will be using later on. Once we have the frequency, now according to classical treatment, force is related to the potential energy by the expression F is equal to minus dV by dx, and if we substitute the values of the force, which is the restoring force, and it is equal to kfx, therefore we get minus dV by dx is equal to minus kfx, or in other words dv is equal to kf x dx. And now if we integrate it, as you can see here, we get ultimately the potential energy V is equal to half kf x square. So now once we have the expression for the potential energy for a linear harmonic oscillator, one can write down the Schrodinger equation. Now let's write about the Schrodinger equation of a linear harmonic oscillator. We already know that the general expression for the Schrodinger equation is h cap psi v is equal to ev psi v, and h cap, which is the Hamiltonian, that is equal to kinetic energy operator T plus v cap. V cap, as we have already seen in terms of potential energy, would be equal to half kf x square, and the corresponding kinetic energy operator T cap would be equal to minus h square upon 8 pi square m d2 by dx2. Here you can very well see we are assuming that the linear harmonic oscillator is oscillating along x direction, and therefore our total Schrodinger equation for the linear harmonic oscillator becomes minus h square by 8 pi square m d2 by dx2 plus half kf x square, all in brackets, psi v is equal to ev psi v. Here psi v is the vibrational state function or wave function. So in this case it will be the wave function for the linear harmonic oscillator. Now out of this Schrodinger equation we need to solve it, and through the solution we will get two things. One will be the vibrational energy ev, and the other will be the vibrational wave function psi v. If you look closely at this equation and compare it with the corresponding equation for a particle in a one-dimensional box, which we have already studied, you will notice that in the case of a particle in a one-dimensional box, we had the equation minus h square upon 8 pi square m d2 by dx2 psi is equal to E psi, because their potential energy was 0. Here we have the potential energy, and that is why we have one more term which is half kf x square. Now our aim is how to solve Schrodinger equation for a linear harmonic oscillator. There are two methods which are normally used for the solution of this Schrodinger equation. One method is the series method and the other is the factorization method. In our this module, we will be discussing about the factorization method to solve Schrodinger equation for a linear harmonic oscillator. But before we go to that method, we should also define, as you have already learned earlier, the boundary conditions for this harmonic oscillator. Here the particle is confined to one dimension and it is oscillating along x direction. Therefore, the boundaries for this linear harmonic oscillator will have x values from minus infinity to plus infinity. That is basically what are the boundary conditions for this example. In order to solve this Schrodinger equation for the linear harmonic oscillator, we need first of all to convert it into an appropriate form so that it can be factorized. So as you can look at this equation, we take this equation, we make a few substitutions, like we put h cross is equal to h upon 2 pi and then multiply this equation by minus 2m by h cross square, so that we get this equation which is d2 psi v by dx square plus then minus m upon h cross square kf x square psi v, all in parenthesis, is equal to minus 2m upon h cross square EV psi v. Now once we have this equation, then we undertake a few steps. First step is we multiply this equation by h cross by m omega, where omega is the angular frequency. And angular frequency, as you know, and you must have studied it, is given by 2 pi times the normal frequency. That means omega is equal to 2 pi nu. And nu we have already calculated earlier. It is 1 upon 2 pi kf upon m under root. Therefore, omega becomes kf upon m under root. So once we multiply with this, we get this equation h cross by m omega d2 psi v by dx square minus kf upon h cross omega x square psi v, all in brackets, and this is equal to minus 2 upon h cross omega EV psi v. So this is the form which we get after undertaking the first step. In the second step, we make a few substitutions. As you can see, the substitutions are, we put y is equal to m omega upon h cross under root x, and this whole is equal to, we say, is equal to ax, where a is m omega upon h cross whole under root. Second thing we do is to make a substitution, lambda is equal to 2 EV upon h cross omega. And once we make these substitutions, our above equation reduces to h cross m omega d2 psi v by dx2 minus y square psi v, all in brackets, is equal to minus 2 upon h cross omega EV psi v. Now this d2 psi v by dx square has to be converted to y variable. And as you can see, this is done through these series of steps. These are very simple mathematical steps, and once you do that and make the above substitutions, Schrodinger equation with which we started gets modified to the final form, which is d2 psi v by dy square minus y square psi v, all in brackets, is equal to minus lambda psi v. So this is the equation now which we have got, and from this equation one can start with the factorization method. That means this equation can be easily factorized, as we will see just now. In order to factorize this equation, we proceed in the following way. We first of all define two operators, a plus cap and a cap. A plus cap is d by dy minus y, and a cap is d by dy plus y. So these are the two operators with which we start. And let's see here that when a plus cap and a cap, when they operate on psi v, as you can see here, we have substituted their values, and using our earlier equation, we notice that a plus cap, a cap psi v ultimately becomes equal to 1 minus lambda psi v. So this is one very important equation which we have got. Please notice here a plus cap is coming first and then a cap. Now we take another way around. One can solve the following case also. That is, we take a cap first and then a plus cap. And when a cap, a plus cap psi v operates, then for this equation, again we solve in a similar way, and we notice that we get another equation which is a cap, a plus cap psi v is equal to minus lambda plus 1 psi v. So these two equations are very important, and once we have got these two equations, you will agree that one can very easily write down the commutator of the two operators a plus cap and a cap. The commutator of the two operators, which is a plus cap, a cap minus a cap, a plus caps all on psi v. If we substitute the values, ultimately the expression which we get is 2. That means the commutator of these two operators is equal to 2. Now in the light of this, we can rearrange our earlier two equations with which we started while finding out the commutator, and one notices that one equation becomes a plus cap, a cap minus 1, then psi v is equal to minus lambda psi v. And if we have a cap, a plus cap plus 1 psi v is equal to minus lambda psi v. So all these equations are basically equal to equation with which we started. Now let's take a next step and let's operate a cap, as you can see here, on the left hand side of equation A. So once A operates on equation A, it becomes a cap, a plus cap, a cap psi v lambda is equal to minus lambda minus 1 a cap psi v lambda. Because psi v will change with lambda, therefore we have denoted here with lambda. And from the commutator relation we know that commutator is equal to 2. Therefore using this relation we find that ultimately we get a plus cap, a cap minus 2 all operating on a cap psi v lambda is equal to minus lambda minus 1 a cap psi v lambda. And this, on further rearrangement, one gets a very important expression. You can see here what we are getting is a cap psi v lambda is psi v lambda minus 2. That means when a cap operates on psi v for lambda value, it will give you psi v for lambda minus 2 value. That is why this a cap, which is d by dy plus y, that is called annihilation operator. So this is a very, very important thing because it annihilates the wave function by 2 units. Similarly, if we operate a plus cap from left hand side, something similar to what we did using a cap, then we notice that we get the equation a plus cap, a cap, a plus cap, psi v lambda is equal to minus lambda plus 1 a plus cap psi v lambda. And if we further solve it using our expression for the commutator, we get an expression ultimately which is a plus cap. When it operates on psi v lambda, it becomes psi v lambda plus 2. Now you can see very well that when a plus operates on psi v lambda, it generates a wave function for 2 units lambda values higher. That means lambda plus 2. Whereas when it was operated by a cap, we were getting 2 units lower. Therefore, a plus cap is called creation operator because it creates higher wave functions. But one thing you must have noticed, whether it is creation operator or whether it is annihilation operator, lambda always changes by 2 units. This is very, very important. These expressions you must try to practice and see yourself that these are very, very important, as we will see later on. Now after having done all this, the question is, what is the minimum value of lambda which is possible? How to get that? We have already seen that a plus cap, a cap psi v lambda minimum because we did it for psi v lambda, but if we put psi v lambda minimum, then the expression will become minus lambda minimum minus 1 whole psi v lambda minimum, and that would become 1 minus lambda minimum psi v lambda minimum. But operating the annihilation operator on psi v lambda minimum, suppose we operate the annihilation, we are already at lambda minimum and we operate on the left hand side with annihilation operator. Naturally, it will give us a zero value because it cannot go to lambda minimum minus 2, that does not exist. Therefore, a plus a cap psi v lambda minimum would also be 0, and therefore one can say that lambda minimum minus 1 will be equal to 0 or lambda minimum is equal to 1. This is very, very important. That means the lowest value which can exist for lambda, that is the lambda minimum, that will be equal to 1. So this lambda minimum is 1. Now one can define lambda in the following way. Lambda is equal to 2v plus 1, where v can have values from 0, 1, 2, 3, 4. You can very well see that when v is 0, lambda will be 1. So this v, we call it as vibrational quantum number. And once we have got lambda, if you remember, we made a few substitutions, and one of the substitutions was lambda is equal to 2ev upon h cross omega. So put it back, and then that is equal to 2v plus 1, and if we make all the necessary substitutions, we get here that the vibrational energy EV, which comes for a linear harmonic oscillator, is equal to h nu then multiplied by v plus half. This is a very, very significant result. That means we can also see here that since v can be 0, therefore the minimum energy possible for a harmonic oscillator will not be 0, but then it will be equal to half h nu v. This is also called a 0 point energy. So you have seen here that we have been able to solve Schrodinger equation and get the vibrational energy expression. So in this module, we have studied the quantum mechanical treatment of the linear harmonic oscillator. We told you that we need linear harmonic oscillator because it is a basic model for a vibrating diatomic molecule. For a linear harmonic oscillator whose vibrations are simple harmonic, potential energy is given by the expression V is equal to half kf x square. We wrote the Schrodinger equation for the linear harmonic oscillator. That was like a particle in one-dimensional box, plus there was a potential energy term here that we substituted, and we got the Schrodinger equation for the linear harmonic oscillator. We defined the boundary conditions, which were from minus infinity to plus infinity, and then tried to solve the Schrodinger equation using factorization method. We used two operators, but before applying the factorization method, we converted Schrodinger equation into an appropriate form so that it could be factorized. And the appropriate form was d2 psi v by dy square minus y square psi v is equal to minus lambda psi v. Then using creation and annihilation operators, we solved this equation, and ultimately we got vibrational energy for this harmonic oscillator, and that came out to be equal to EV is equal to h nu v plus half, where v is equal to 0, 1, 2, 3, etc. Now, in the next module, we will discuss how to get the wave function for a linear harmonic oscillator.